Hello,
Yes, sir.
am I audible?
Yeah, yeah.
Okay. Hello, hello.
Yes, sir.
So in this week, sir mostly discussed about uh, what it is called statistics type things like photon statistics, or how can we?
Sir,
Hello,
yeah, before you start, I had a request.
bolo.
So the lecture slides that sir is teaching for week 8, 9, and 10, those slides have not been uploaded.
Okay.
So we are having some difficulties during solving those assignments. So if you ask sir to upload those lecture slides, that will be very helpful for us.
Uh, Give me 1 minute. Okay. Which week? Week number
Week
8, 9.
8, 9, and 10.
Okay, I have message to the sir. Maybe he will reply, or I will let you know. Okay, is it okay? I just messaged to the sir. Okay, so in week 9, mostly the uh, terms used to photon statistics, or like how we can explain the light in terms of statistics. Like because if you know the light only. Hello, are you able to see the screen? Okay, so in the waveform the light can be expressed like E naught sine kx minus omega t plus phi, like that. Okay, so this is somewhat you can say that in classical electromagnetic theory this is the ideal source of light with constant intensity, which is E naught, and the spatial and temporally coherent electromagnetic waves of some single frequency. Okay, if you vary this omega from omega 1 to like that, then you can change the frequency of that light. So this is mathematically used. So but phi is here time independent phase shift. Okay, so like how can we, this is somewhat the classical representation of the light. Okay, so how can we represent the light in quantum nature, like in quantum mechanics, in the way of quantum mechanics? So there is one word like coherent state. Do you know what is the coherent state? Because if you present some light, maybe we can talk about coherence of the light, and this coherent state can be of two types. One is spatial coherent or the temporal coherent. Okay, so let's talk about spatial coherent. So how can we, in quantum mechanics, how can we represent this coherent state? So analogous to that, if let's say this is one state, some state alpha, it denoted by coherent state, and it is described by summation over some state like n equal to 0 to infinity and alpha to the power n root n factorial e to the power minus alpha square by 2 and some arbitrary state, let's say n. Okay, so where this n is some distinct feature of coherent state. Okay, so if we project this coherent state onto the fog state, one it is called fog state. So what it is, fog state?
Is it, sir, something like
This,
some
yeah,
intensity variation like in we observe in spoons or forks like that?
yes, like this fog state we represent by this n here. So in quantum mechanics, if you say the fog state, or it is a number state. Okay, so this is a number state, and this is also a quantum state we study in quantum, like 1 2 like that we represent now first state or second state like that. So is in an element of Fock space. There is some Fock space called some mathematical, you can read more. So with a, this is a well defined number of particles. Okay, so Fock space what does it does define the number of particles. Okay, because if you know that this light is something quantized with this photons, right, in quantized energy of photon. So then if it is quantized, then there comes some number. Okay, the number of particle and number of photon we say. So so we, for this number of particles we can define in this Fock space, where is some state, there is number state, this is delta n. Okay, so maybe you can say this number of particle of the same energy in the photon. Like if you have 532 light, okay, so there are every photon or every quanta of this much energy. Okay, sorry, this is lambda in nanometer. So it is something correspond to this some E, right? So number of particles there will be there if we quantize the light, that you understand, right?
Yes, sir.
So that number of particles can be defined in mathematical terms by some Fock space. Okay, so in that Fock space there are some elements, say n, which defines some number of particles, and the space it is like on the name of some scientific Vladimir Fock. Okay, so this is some quantization formula there to represents the light in quantum states. So if we can find the probability of this state n, okay, so this comes with some Von rule. So this Von rule, what is this Von rule? So this is a some Von, you have heard this name Von, right? Max Von. So like the what is this Von rule? This is some postulate in quantum mechanics, which gives the probability, like this gives the probability that a measurement of a quantum system will yield a given result will yield means if we say in simple form, so we can say that it states that the probability density of finding system in a given state. Now is it clear?
Yes, sir.
Yeah. So this Von rule is a postulate which gives you a probability density of finding any system in a given state, whatever state is given. Okay. So that if you have some state, this coherent state, so probability of finding that coherent state can be given by some this alpha to the power 2n divided by n factorial e to the power minus alpha square. Okay, so if you solve it, So it will give you some average number of this n to the power n divided by n factorial and e to the power minus n. N is the average number, like you can say. So this results known as a Poisson distribution, a Poissonian distribution. See, this is more on what it is called, theoretical side of the photonics, say quantum photonics. So if you calculate this delta n square is equal to this n, this is some distinct coherent state that is given. So you can find the probability density of that state to be a coherent. Okay, so from this concept, this type of light, like we have light, first we analyze this light represent by this formula only. Okay, so this is in classical form. Then when we come to the quantum light or quantum photonics, so now the some state which is coherent state can be described by this formula, and this is stated by some Fock state and the Von rule, by some Von rule, and with that state what will be the probability density of finding that, like all the quantum mechanics is based on the probability, right? There is not exact things is there in quantum. If you find the result, so you are not getting the exact, that is the result, that is the probability of finding in that state. Okay, that quantum mechanics states only. So so this is the probability distribution you can give to give some what it is called quantum photonics. So like this is also known some this from this formula you can say this is a Poissonian light. In same way there are many types of representation, some called super Poissonian light, or you can say one is sub Poissonian light. So all these type of lights comes under photon statistics. Because photon is countable, right? So this is, there is some number of photons, so there is some number state should be defined. So we can say statistics, like how much number of photons at which state, like that. So that defined by some probability density. Okay, for example there is some beam splitter, it is called beam splitter. So you know what is the beam splitter? So beam splitter is one which, if you fall some light on this one, so some of light will go this side and some of light go this side. So if it is 50-50 beam splitter, so this will be 50% intensity will go this side, 50% intensity will go this side. And if we put one another beam splitter, okay, so half light will go this side, half light will go this side. Okay, and if there is some detector and here some is detector, okay, and we can count. So if quantum mechanics, in quantum mechanics the light is in quantum state, so we can say we can count the number of photons. So let's say in this light, in this line there are some number of photons will come, right? And then these number of photons will go this way or this way. Okay, so if you count on this side, some photons only countable in this side and other will go this side, right? So number of photons will decrease in this line, and if it is 50%, then half will go this side and half will go this side, but we cannot say which photon will go this side, right? We can only find the probability. What probability if only one photon comes from this side, so it will either go this side or will go this side. Okay, so the probability is half. Probability is that photon can be counted by this detector is half. A probability of counting that this detector will got that photon, the probability will be half. So this is type of correlation. And next sir also discuss about second order correlation, that is known as G2, right? This is very hot topic in the research for now in photonics. G2 measurement of single photon emitter. You know this?
No, sir, I'm not aware of this.
Yeah, so this is very hot topic in the photonics, the single photon detector. So this single photon detector all are measured on the basis of this G2 correlation. So for that, this photon statistics is very crucial for that thing, because in quantum mechanics we are talking about single photon, right? So if single photon comes to on this beam splitter, this will go either on this side or either in this side. Okay, but in classical, if you go to the classical light, so classical light at a single time there will emit many of photons. You cannot count, like you can count, but there are number of photons at the same time. So at the if same time, let's say 10 photon comes on this thing, then what will be there? Half will go this side and half will go this side, right? So that is in classical only. But if in quantum mechanics, if we come, so if at a time there are only one photon, then that photon, what will happen at this beam splitter? Either that can go this side or this side, right? It cannot be half photon will go this side, half photon will go this side. Is it?
Yes.
It can be happen.
Yeah, quantum mechanically it is not possible.
It is not possible. So that photon will be detected on this system, that the probability will be half, or the probability will be half, it will go at this time. So that is related by this G2 correlation system. Maybe sir explain little bit more, like the intensity at some time t and intensity at some t plus tau. So we take the average, and then something I t, and what is in the denominator, I not sure, something like this one.
Yes, sir, average of those two.
Yeah,
Individual averages of these two.
individual averages of these two. Okay, so see, at a single time we are saying that if photon emit at time t or t plus tau. Okay, so it can, if there is single photon, then either it will emit at t and t plus tau. So if t plus tau, no, this will be this tau is the time interval of emitting those two photons. So in between there is only one will be 0 or one will be 1. Okay, so that G2 will be 0, and if G2 is maybe some number, if it is emit at the both time t and t, then it will be 1, then it is a significant there is no single photon emitter in this system. So this is the some concept of single photon emitter, which is related to this quantum photonics, and also with this photonic statistics we say. So sub-Pesonian light, sir have some showed you some condition that this delta n square, which I described earlier, is less than this state, right?
Yes, sir. Delta in, yeah, for subposition.
Yes, suppression statistics cannot be described by the classical electromagnetic theory. All this Pesonian light is the concept of quantum photonics. Okay, so this advantage of this ultra fast photo detector has made it possible to measure the sub-Pesonian light nature of the light, because we are saying the detector, so these are not the normal detector, these are very uh, ultra fast detector, or you can say very precise electronics can be is used in this one, in the order of some femtosecond. Okay, so this much fast detector you need for detecting a single photon. Okay,
Yes, sir.
so these are some initial concepts which maybe sir described in more detail. So comes to some uh, tutorial part. So we have question number 1, this photon status of light describe. So what you understand about photon statistics of light, what it describes mostly?
So it, like the number of photons that are being emitted from the source on or detectors that they are
Okay,
carrying.
right. So I am writing the options, you can choose in this one. Fluctuations in light field of light. B is the quantum efficiency of detector. And C is the fluctuation of photon number per unit time. Yeah, per unit time interval we can say. And D is the photon intensity of the light beam. And E is the photon energy of light beam. So which answer you will choose?
Yeah,
According
option C.
option C. Why?
Because we are dealing with the number of photons.
Okay.
Either it is emitted from the source or it is going to a channel or something like that,
Yes.
and their statistical
So only
characteristics.
we deals with fluctuation of photon numbers. Okay, for a time interval, because here if you see the correlation function, there are some tau. This is the time interval between two photon emission, right? So we can
Yes.
use the fluctuation term fluctuation of photon number. Similarly, if, the second question is in Pesonian light, the standard deviation of photon number around a mean value is given by.
Yeah, it is square root of n bar.
Hmm?
Square root of n bar.
Yes, standard deviation of photon number around a mean value is given y. Okay, so this is you are saying square root of n. This is the answer only, because we are choosing in probability mean root mean square value, right?
Yeah, and for
So
the Poisson distribution, it is the standard deviation is square root of mean.
yes,
From there,
sigma square is the deviation, right? Then we choose the what is the deviation, that is under root that of that one, right? Whatever it
yes,
comes.
sir.
So that is the under root of n. The other option are also there, not needed, but like 2n var or 2n var square n var.
Sir, if you don't mind, like,
Yeah.
can you just copy paste the question and the options? I think that would be very helpful for you also.
I do not have in this device the questions.
Okay, okay.
Next time I will try to get in this device so that
Actually, sir, one more thing, like I can suggest, like if
Yeah.
you just keep the questions in each page, just copy or take a screenshot and put them on each page.
Okay,
Like,
okay, I will try.
that will be very easy for you. You don't need to write every time.
So this question 3 is, consider a beam of light, this photon energy, that is 2.0 electron volt, okay, with an average power is 1 nanowatt. Okay, so this is the common data for next 2-3 question. So first you have to calculate the photon flux. How will you calculate?
Yeah, the photon flux should be total power by power of each particle.
Yes, so this
So-
photon flux can be defined by power divided by h cross
H.
omega.
Yeah.
Okay, so that is also we can say photon per second. So the power is given by here 1 nanowatt, right? And h cross omega, so this is in watt, right?
Yes.
So this energy should also be in watt.
Yes.
So this is given 2.0 ev, right?
Yeah.
So for ev you can calculate 1.6 into 10 to power minus 19. This will be in bold, and here you can write this 1 into 10 to power minus 9 watt. So if you this convert by in some joule, I think it comes joule or
I
watts.
think the denominator would be joules.
Sorry.
The denominator, that is in electron volt, that you have converted na 2 into 1.6. The unit
Yeah.
will be joule.
So what the answer will come around?
It is approximately
3.125 into 10 to power 9, right?
Yes.
So this number of photon per second will be the photon flux for this given beam line. Similarly, if you say number of question 4, the count time of 1 nanosecond will contain an average of photon. So what will be the average number of photon?
Sir, here I have a question.
Yeah.
Like the same question has been given in my assignment also. Okay, so what is the definition of count time? Because this is not covered in the lecture.
What is the count?
No, the count time, the term count time, what does it signify?
Yeah, this count time will signify like if you use some spectrometer, right?
Yes.
So how does spectrometer works? Like in optics, like the number of photons are connect falls on the photodetector, right?
Mm-hmm.
Then it generates some electrons or some some current, you can say. That current is measured by the electronics part of the detector. So uh, what is the current for one photon? Okay, so that count time means for what time you are counting that photons. Like after the detector there are some slit or there are something. So if you set the count time means 1 nanosecond, so in 1 nanosecond whatever the photon will come on the detector, that only detector will work. After that that detector will dead, right? Not dead, it will be off.
Okay. Okay.
So that time interval is the count time, for what time the detector counts the number of photon, because number of photons are coming on the detector for all the time, let's say. So but if you off the detector it will not count, so the electronics part will be off, right?
Okay, sir.
So average photon in this count time, so this count time you can say this is some tau, right? So tau is given 1 nanosecond, and the flux is given, we are calculated in the above one, 3.125 into 10 to power 9. Then the average photon in count time will be 5 multiplied by tau. So you can write 3.125 multiplied by 10 to power 9 into 1 into 10 to power minus 9. So there will be 3.125 photon in per nanosecond, if you say no, in 1 second, in 1 nanosecond, right? But number of photons will be this should be like
Integer.
integer. So there should be answer only 3, we can say. What whatever in answer there is, this is the option straightforward, so you can choose that one. But sometime if you are not finding the exact, then you can maybe take the greatest integer function, right? Know the
Yes.
greatest integer function?
This in this case it will be 4, I think.
In greatest integer function, no.
That's a greatest integer function.
uh,
Uh,
it will
uh,
give the, it gives the whatever the integer part, the highest
okay, in
integer.
that case it will be 3
Yeah.
if you omit the decimal part.
Hmm. So next question number 5. A segment of the beam with a length of 3 meter correspond to the count time of. Length time, length, sorry, length of 3 meter corresponds to count time. Your options are 3 second, 1 second, 1 nanosecond, 2 microsecond, 3.3 nanosecond and 10 nanosecond.
It would be 10 nanosecond.
10 nanosecond. And how you calculated this? See, this is some light beam. If you say for some length L, it is reaching at this point, right?
Yes,
This is
sir.
your detector. So how much time the last detector will take to reach the detector will be the equivalent count time, right? If you
Yes.
cut the line from here, so whatever electron photon will be there will reach at this point. So this much longer time you have to open the shutter. Okay, so that this last photon will reach on this one. The time you can calculate it by the formula T is equal to speed, sorry, whatever the length is divided by the speed. Okay, so length is given 3 meter, and what is the speed of the photon?
It would be 3 into 10 to the power 8 meter per second.
3 into 10 to the power 8. Okay, or you can say if we put some media in this question, then the what will the speed
Divided by n.
divided by n, right? So n will be 1, so you can use 3 into 10 to the power 8. So this is around 10 to the power minus 8 second, or you can say 10 nanosecond. Similarly, question 6 is given a beam segment of 3 meter will contain an average number of photon. The options are 312.5, 3.125 into 10 to the power 5, sorry 10 to the power 9, 3.125 into 10 to the power minus 8, D is 2 into 10 to the power minus 9, E is 2 into 10 to the power 9. What will be the answer?
Sir, we already have 5. From there, we know that the in per nanosecond, per
Yes.
unit time, how much
Whatever the
photons
average
are passing.
time will be 5 multiplied by tau, right?
Yes, yes. Mm.
So this phi is given 3.125 into 10 to power 9, and tau is given 10 into 10 to power minus 9 for 3 meter segment, right? In the
Yes.
previous question we solved. So
Mm.
simply it will cut, and this give 331.25 average number of photon. Question 7 is photon statistics of coherent light wave with constant intensity is given by subpasonian distribution, B superpasonian distribution, C is Pasonian distribution, D is Gaussian distribution,
Yeah, it will be option C.
E is Lorentzian distribution, and D is binomial distribution. So I just explained you. This will be the distribution for coherent light. Uh, Poisson distribution for mean value 0.1, 1.5 and 10. Okay, sorry, 0.1, 1 and 5 and 10, these are given. So how can you plot? So this is 0, this is 5, 10, 15, 20. So this is giving like so this is around 0.2 and this is around 0.8. So this is some bar, you can like that. Sorry, similarly like that. This is some probability function, you can say. Similarly it is given 0 to 5, this is 0.3, 0.2, 0.1, 1, 2, 3, 4. This is fifth one. So these 5 columns are till 0.5. Similarly, it is given like 0, 5, 10. So this is given something like that. The maxima is goes to here, and then it is decreasing at this side, and also decreasing it at this side. Okay, similarly this is giving fifth one till 0.1, 0.05, and maxima goes to like this and decreases value. And at this side also this is decreasing uniformly. So something this type of shape you can consider. This is 20 and this is 0. Similarly in this one you can consider shape like that, and this one obviously this type of. Like that. Okay, so now the question is, the probability distribution has its peak. At what? Root n average, n average square, n average by 2, or n average by n. So probability distribution peak, talking about this, what is the relation between this peak and this n value? At this axis there is n, at this axis there is probability. So this is for n equal to 0.1, this is n equal to 1, and here n equal to 5, this is n equal to 10. Okay, so this is the value of 10.
Occurs at the in bar, I think.
Yes. Peak value at n var, because if you say 10, so what is the n var?
Or A equal to 10. It is 10.
Hmm?
For n equal to 10, it is 10. Around.
This is n equal to 10, and here is something around 0.1 only.
Yeah, the fourth one.
Not fourth one. You have to find the probability distribution has its peak with function of the, at what function this peak value will change.
Okay, so it will be the option B.
Option V, right?
Yes.
Because this is the condition of Poisson distribution, right? So this is the answer. So the next question is, with increase of n var, the relative size of fluctuation photon in photons flux, what will happens to the full fluctuation of photons if we increase the n var value? It will decrease, increase, unchanged, data insufficient, so what will be the answer?
So it will decrease.
Eh?
It will decrease.
On what basis you are saying?
Okay, the mean number of photons is defined by delta n by n bar. And
Delta n by n
n
var.
bar.
Yeah.
If we increase it, so it will obviously decrease, I think.
Yeah. So this is the relation. So from which you can say that this decrease with increase of n var value, the number of photon counts. Now question number 10. Match the types of light with its corresponding photon number distribution. Types of light with its corresponds photon distribution. So these three are H, Subpasonian, light or super Pesonian light, and in between there are Pesonian light, right? This is B, this is C, and here is given the distribution delta n equal to root n var, delta n less than n var, delta n greater than n var,
Okay, 3 will be C, and option 2 will be A, and 1 will be B.
so A will be
Option A. Option A will be B. Option 2.
this one, option 2. So delta n should
Less than
less
N bar.
than root n var.
Yeah.
Okay, and what will be the matching of V?
B will be 1.
V will be 1. I just earlier told you. And what is the C?
Yeah. C is 3.
3. So this is the Pesonian, right? So Pesonian, in Pesonian there is under root delta n. So these three are not valid answer. So like in these three, so Pesonian means equal, सब छोटे की तरफ आता है ना, like so you can say delta n less than, and super means higher, so this delta n greater than this one, so you can remember like that. Sub means छोटा, super means greater, so this delta n is greater than it is super Pesonian, like that. So question 11 is given, choose the detectors that are typically used for single photon detection. SPD लिखो, you single photon detector. So options are single photon, avalanche photodiode, V is photomultiplier tube, C is silicon photodiode, D is phototransistor, E is photoconductive detector, F is volumetric.
I think, sir, this is not covered in the 9th book.
This is not covered.
Yeah, I haven't gone through this.
Okay. So photo multiplier tube, you know what it is?
No, no, I can understand that the avalanche photodiode I can understand that it can be helpful, but photo transistor, photo detector. I think option one could be possible.
Okay.
What others I don't know.
Yes. You choose right answer with your common sense. Not common sense. You have must read about these things. So see, silicon photodiode is little bit for normal range. Okay, mostly silicon photon diode is used, but not for single photon detector. And some are used photoconductive detector also. But for single photon detector, there are these two: single photon avalanche photodiode and photo multiplier tube. So in this SPAD, it is abbreviated as SPAD. Sorry, AD. So in this one, this is also in the family, comes under the family of avalanche diode only. What the difference is, this SPAD is based around a semiconductor PN junction. So what is the meaning of semiconductor PN junction?
This one side is P, another side is N type.
Around the PN there are some semiconductor. Semiconductor is the PN junction are semiconductors only, right?
Mm-hmm.
So the PN junction diode, it can illuminate with the ionizing energy radiation, such as gamma or X-ray. These are some ionizing radiation energy. So beta or alpha particle along with the wide portion of electromagnetic spectrum. So from UV to IR, right? So this is little bit sensitivity is much higher than normal avalanche diode.
Okay. And how this photo multiplier tube works?
Sorry,
And option B, you ticked on the option B, na? Photo
photo
multiplier.
multiplier tube. Okay,
How does it
so
work?
I will just brief what is SPAD. So like if you see the structure of this one, so this will be like let's say this is the region of P plus, this is the region of P type. Okay, so there will be some material below that. This will also be P plus type, and this will be, you say, N plus type. Okay, so what is the, this will be N plus, P and P plus. Okay, so this is something avalanche region of 1 to 4 micron, you can say. Okay, and there is something, you can say, some and this is some gate from which the photon can enter, and this is around approx 10 to 100 micrometer wide. And if you see the characteristic of this for current voltage, so let's say this is I and this is V. So this some reason for linear amplification, right, from here to here. Let's say if we apply the voltage, but after that it starts increasing current. Okay, so this region is for APD, in which the linear amplification will work, but here there is some thing which increased little bit. So in this region this as PAD, but so this is on branch, then SPAD on, and this branch is called off branch. Like if the voltage at this voltage current is this much, if photon comes then it is on, and if photon did not come, this is in off stage, right? Understood little bit?
Yes, sir. Yes.
And for if you go to for the this photomultiplier tube known as PMT, okay, so these are also some extremely sensitive detectors of light in the region of ultraviolet, visual or near infrared region, but there are some numbers of class of vacuum tubes. More specifically, if you say vacuum phototubes. One minute. Sorry for interruption. So these are some specifically vacuum phototubes. What it have, as per the name, multiplier, right? So if one photon comes there, then it multiply the number of photons by some mechanism and detect, and then if you divide by that multiplier, you will count the exact number of photons which came at this one, okay. So the if you see the photo of this photo detector PMT, so it will looks like something like a long tube is there, and in this tube there are some this photocathode, okay, and some focusing electrode, okay. So there are some window in between here to click out the photon, and you know the dynode. I also did not know exact what is the meaning of this dynode or anode, okay. So there are some diode anode of arranged in this one, and when electron comes from here and go at this one, then go from here to here, like that. And at when it comes only one photon, like then from another anode it multiplies 2. When 2 comes, it emits 4 from this anode. Okay, and then it comes here, then 4 to 8. Like if it is comes 1 here, then 2 here, 2 का multiply 4, then 8, 8 to 16, 16 to 32, like that. Okay, and there are some pins connected to here which can measure the current, like go to. So this is some schematic of a photomultiplier tube coupled to a scintillator. This arrangement is for detection of gamma rays. Okay, and also like the connector can be connected like that here. So there are some ionization track are there, so that when ionize and go to this photocathode, it emits some current, and that current is measured, electron is measured in terms of current. Okay, so if you say the photomultiplier voltage divider circuit, it will look like something. This is photocathode. Okay, and here is some anode. Okay, so it will look like here are some high voltage. Okay, so there are some diodes are there which we are giving here. Okay, so it will something this R, and then again R. So these are resistant, and they are not that much. Here are some multiple diodes. Okay, and then after some there are some capacitors type thing, and here some R out. There is the load we can connect, and here is grounding, and this goes like that. Okay, so like if we have this resistance value around 100 kilo ohm and C is 0.1 microfarad, so this is some equivalent electrical circuit of this photomultiplier tube called KPMT, and this is some schematic you can see. So, and if you see the working, you just like you can say that there are many multiple diodes are there which multiply the electrons which are generated by the photo cathode. That's why the name is photomultiplier tube. Okay,
Okay, sir.
so these are two types of detectors which can be used in single photon emitter detector, single photon emitter. And question number 12, we are on 12, right?
Yeah, previous one was 11.
So there are one photostatics, and classical equivalent. So there is Passonian, and B is Passonian, and C is sub-Passonian. And there are none, that is non-classical. 2 is partial coherent, incoherent, or thermal light. Okay, third one is equivalent to perfectly coherent light. So as I told, like in quantum mechanics, the light can be divided in three types of statistics: Pasonian, super Pasonian, and sub Pasonian. But what will be the equivalent to the classical? So Pasonian light always use the coherent term, right? It is
Yeah,
depend on.
we go to
So if the perfectly coherent light, if we are seeing in a classical, means quantum mechanically it is Pasonian light. If we go to the quantum, like we called perfectly coherent in classical reason, means that light we have to get from Pasonian distribution in quantum mechanics. Okay. Similarly, what is the equivalent to the super Pasonian?
it will be partially coherent.
Yeah, partially
Thermal.
coherent or incoherent, or the thermal light, which the thermal light is non-coherent, right?
Yes.
That's incoherent. So all these type of lights in classical reason, if we go to the quantum, these are equivalent to super Pasonian light. Okay. Similarly, sub Pasonian light is, we can say, non-classical. We are not talking about coherence or non-coherence in when we talk about Pasonian light. Okay, Pasonian light, sub-Pasonian, we can say that this is the bridge between classical and quantum, in between. So not not the perfectly classical light can be there, or maybe non-classical, we can say non-classical to equivalent to sub-Pasonian light. Okay, so the final answer after this will be 1 2 3, sorry, a 2 3, sorry, a 2 2 and v 2 3 and c is for 1. So this is the perfect match for this type of question. So question 13 is, in regards to a photo detection process, arrange the following sequence of event chronologically order. Okay, photo detection process. See, E1 is triggering the release of more electrons. This is one process in between photo detection process. Second process is generation of current pulse. And third one is interaction of light with the atom in detector. E4 is given liberation of individual electron by the photoelectric effect. You know what is the photoelectric effect? Or illumination of light beam.
Sir, in this question, like I have a confusion in between.
Sorry.
In this question,
uh,
actually, I have a confusion in between the
Bo-
option three and uh, sorry, just give me 1 second. Two. Yeah, I think option five would be the correct one.
Not
Last
no,
option.
no, no, no.
E5, E3,
No, no.
E4.
The question is, these are all the process of photo detection. Okay, step of photo detection process. So you have to chronologically order. You have to arrange all these process. In
Okay.
the whole photo detection process, what will be the first? First, we illuminate the light to the photo detection. Okay.
Yeah, E5.
So this E5 will be first, then
Then E3.
E3, then
Yeah.
that light interacts, that interaction of light with the atoms in the detector. So it
Yes,
will
sir.
come at the second step. What will be
Hmm.
next?
It would be E4.
E4,
Yeah.
then liberation of individual electrons by the photoelectric current.
Yeah.
Okay, liberation means change, right?
Yeah.
Uh, then after that,
Now I have a confusion in between E1 and E2. So
what?
which one will come first?
What is the generation of current pulse?
Yeah, actually, I have the confusion in that term only. Like,
Okay. Next, and E1 is triggering the release of more electrons. Okay.
hmm.
So E1 will come first, and then E2 will come. Okay.
Oh,
So why it is, like for example, if we take APD or avalanche photodiode, okay,
mhm.
or a general photodiode. So in avalanche photodiode there will be some intrinsic region, okay, and some p type and n type, okay.
Okay.
So if let's say this quanta of photon comes on this intrinsic part, because this is the, or this part is called, not this part. So maybe some photon quanta comes on this avalanche photodiode. What it works like, as we say, first light will emit. This is a part of E5. Okay. Then the interaction, this electron, whatever the photon will go inside, it generates some uh, one hole that is plus, and one electron that is minus. Okay, that is the interaction, that is the part of interaction of light with the atoms in the detector. Whatever
Mhm.
quanta comes, it is split the hole and electron. And if you have some battery, okay, this this electron, sorry, this is positive, this will be negative. This electron goes to the positive side, and this photon will go to the negative side, attracted to negative side. So that will be the generation of electron. But one photon can be absorbed. Then if only one electron can be generated, can it reach to only one electron here to here?
No, no. In that case, we need multiple.
Multiple triggering and release of more electrons by scattering or some process of this electron, right?
Yes.
So in this sense, this E1 will come first before generation of light,
Yes. Sir.
sorry, generation of current pulse. Now you are clear with E1 and E2?
Yeah. Yeah.
Okay. Then comes question number 14. So question number 14 is given 10 milliwatt of helium neon laser beam operating at wavelength 632.8 nanometer, okay. It is incident on photodiode with responsivity 0.43 A W minus 1. So calculate the quantum efficiency. Efficiency of photodetector. Just see and solve. I will come in 5 minutes, just for 5 minutes. Okay.
Okay, sir.
देवनीता 10 मिनट के लिए गाने वगैरह बंद कर लो प्लीज, थोड़ा मेरा क्लास कंप्लीट हो जाने दो। वैसे वो भी बंगाली लड़का ही है जो पढ़ रहा है, वो भी बंगाली लड़का है, अगर बंगाली गाने बजाओगे तो उसको अच्छा लगेगा। हेलो हेलो got any idea to solve this?
Sir, responsivity, I think it would be
Okay,
the
going right.
amount of power that has been incident on the system into the quantum efficiency.
Yes, so this will be around eta E divided by h cross mu. This is the formula for responsivity. Here this is eta is quantum efficiency, E is electron charge, h cross omega is the energy of photon. Okay, So energy of photon, if you calculate it in h cross omega, so this will be an eta h cross, sorry, mm, we just calculate, we have to calculate this eta, right? So eta will be h cross omega r by e. So this will be h cross c by lambda into r. So just r is given 0.43 a watt inverse. H cross will be 6.63 into 10 to the power minus 34, and c will be 3 into 10 to the power 8, and it will be divided by 632.8 into 10 to the power minus 9, because this is the nanometer, it comes here, and 1.6 into 10 to the power minus 19 will be the value of electron E. So do you have calculator?
Yes, sir, I'm calculating.
This is minus 34 and 8, this will be minus 26, and minus 19 and minus 9, it will be minus 28. Okay, so it will be 10 to the power minus 2. Okay, and 632, 6.63, 0.43, all it will give you,
Yeah, it is coming around 0.84.
yeah, 0.084. So it will be around 84% will be the quantum efficiency, because quantum efficiency is in percentage, right? Then it is 84.4%.
Sir, like, what is the use of this 10 milliwatt power that has been given at first?
10 milliwatt power, there is no use from this formula.
Okay, okay,
This is for your confusion only.
okay.
Sometimes some extra information we give to confuse the student, because otherwise sometimes you can see the method of solving, you can have an idea of the formula by some what it is called unit, what you are finding, what is the unit of this one, and what is the unit of given parameters, you just arrange according to that. Sometimes you will get correct answer, right?
Okay.
Here I think there is no use of 10 milliwatt.
Okay.
So these were the questions for today. If you have some question.
Yes, sir. Can I share my screen? Actually, I have some queries from the previous assignment, assignment 8.
Okay.
Can I share my screen?
Sure.
Okay. Sir, can you see my screen now?
Yes, yes.
Okay. Sir, I have a query in this question number 5. Okay.
Okay.
So, as you can see, like, you have also given an example of this kind of problem. Okay. Here, like in this case, uh, as you can see, like in figure 2, they have asked to tally the
In curve C of figure 2, we do not observe an oscillation in the probability of finding atoms in the excited state. This is because, huh? Then what is your?
Yeah, actually, sir, here this option that gamma equal to omega r and low q value, okay,
Hmm.
q cavity. This is also correct, right? Because in the class also when sir taught us, he didn't mention anything about the gamma greater than gamma greater than omega or something like that.
Hmm.
So here that's why I choose this option that gamma equal to omega and low q cavity, as
Okay.
you can see from this card. Okay.
Uh huh.
uh, so here also when sir taught us, he the card C he mentioned as gamma equal to omega r. Okay.
Yes.
So accordingly I have chosen this option, but on
The
the correct
gamma equal to gamma equal to omega r and
Mhm.
low q cavity, and this gamma is damping rate.
Yeah,
How?
yeah, everything is same, everything is same that you have taught us in your lecture
Okay.
also.
Okay.
This is the figure.
Hmm. Yes. That I.
So,
Okay.
why this gamma greater than omega is only true? Because this option is also valid as per our understanding from the classes and your lectures also.
Gamma is damping rate, and if damping rate is equal to the exchange rate of energy, so oscillation in probability of finding atoms in the excited state. See, in excited state the probability is zero in the lower case because there are low Q cavity. So low Q cavity means damping rate of cavity will be also higher, right?
Yeah, but it starts from gamma equal to omega, na?
Gamma equal to
Omega. From there we get this kind of behavior.
no, like in this gamma, I told you that this omega should be equal to addition of this damping rate gamma plus this cavity or something material loss also, right?
Okay.
For the strong coupling. So that term, if you will add in this one, then this will be in what it is called B coupling region.
Yeah, actually, that is the main thing. Like when sir taught us, he completely discussed about this gamma equal to omega r. Okay,
Okay.
so accordingly, I have chosen this option, but suddenly it is showing like this. Even it is
Uh,
not a multiple choice option also.
yes, that is okay. So can you that one channel is there for discussion channel, right?
Okay, okay, fine. Okay, fine.
Can you raise the question on that one because sir also see that. Uh,
Okay, fine. I will raise this issue.
okay.
And another thing is, yeah, in this question. Okay, question number 7.
Okay.
Okay,
Consider a
so
three-level gain system as shown in figure 4. The absorption and emission transition frequencies surrounded by omega 1 and omega 2, respectively. The lifetime of the carriers for the transition between energy levels tau if and subscript I and f denotes the initial and final energy state. For which the following lifetime of different energy levels do you expect to achieve population inversion? Okay, so
yeah, actually, this option is correct that I have answered here.
yeah,
Okay, and accordingly, there is a connected question in question number 8. Okay,
okay,
so where as in hint, he has mentioned that width of the spectral line is inversely proportional of the lifetime.
hmm,
Okay, so accordingly, what I have done, question number 8. Yeah, I have chosen the option A. I think. Yeah,
yeah.
but here it is given option B. So how this is happening? Can you just
Uh,
explain?
but they ask referring figure 4, the absorption and emission spectra of the sum of gain material are plotted in figure 5. Sum of the gain material plotted in figure 5. Okay. Choose the gain material that is best suitable for laser application. Okay. So laser, you choose A.
Yeah, yeah.
What is your
Because
logic? What is your
but
logic?
here the spectral line is inversely proportional to the lifetime.
Lifetime.
Okay.
Okay.
Now tau 31 is the highest. Okay. So
Uh,
accordingly, it would be a fine line, the tau 31. Okay.
yes.
Since it is inversely proportional,
Uh,
then it will come the nanosecond portion, that is tau 21. So
2 1.
tau 21 would be for the spectral
E21.
line would be wider.
E21.
Yeah,
Okay.
E21. So accordingly, I have chosen this A.
Okay.
So actually, see, for laser application, this B is suitable. That I can understand this due to this small line width and all. But the this hint created some confusion here. Okay, if I follow this hint,
Mm-hmm.
okay, so as you can see directly from these options, the option A would be the correct one.
And where is E32?
E32 it is not given here.
Okay.
As
Just comparison between E1, E31 and E21.
yeah, yeah.
Mm. Figure 5. See, E31 at the lower energy, right? Emitting at a lower energy, and see, absorption and emission spectra of the sum of the gain material. So the what is the absorption and what is the emission? Just go to the spectral line. Yeah.
Yeah, here
So
absorption is happening
E3
from 1 to 3.
absorption is E31 goes here to here,
Hmm.
and emission is E21.
Yeah.
E21. Okay. So if absorption will be at lower energy,
Hmm.
okay, and this will be the tau 31 and this will be tau 21. So lasing will be due to this reason, right?
Yeah, from E2 to E1.
So E21 will be the lasing peak, not the
Yeah,
E31,
yeah, right.
because in E21 there is a population inversion, will be population inversion. For E31 there will be no population inversion, so your laser will be die after some repetition.
Yeah, that I can understand, but as you can see, the hint that has been given here, okay.
So they give the hint here because you just have to find that the find there is no much interpretation from here. You just have to have find this tau 31 and tau 21, 1 nanosecond and 1 millisecond. Okay.
Mm-hmm.
So but in all these figures they are not depend on this tau, the given tau 1.
Okay.
Okay. So you from here you can say like there is the very sharp line, so q factor will be high here. So q factor will be very high, that will be the laser. Okay.
Okay.
From this one you can complete this one, but E21 will be the higher because E21 will be the lasing peak. So either figure B or figure this, sorry, A B C D E. E you can also choose because E2 at E21 there is a lasing peak is given in the figure E also, and then why not but E21 is a higher energy to the E31, right?
Mm-hmm.
So that's why this is wrong according to above spectrum. E21 will be less, so this is the relation or code. E21 is less than E31, and also the population inversion is uh, what it is more suitable for this E21 because E21 is the E2 is the middle state, metastable state, you can say.
Mm-hmm.
That's why they give the answer B.
Okay.
If E31 will be the laser, you just go to the atomic of this one. Okay. So lasing can happen between E3 to E1 also.
Yeah.
but there is no population inversion
Inversion.
state above
Yeah.
E3. So
Mm-hmm.
this will give you only the short pulse of lasing. But
Okay.
if E21 will be give you the lasing, then it will be continuously for long time, because the population inversion from E3 to E2 will be happen there. So there is a good population inversion in E for E21. That's why they give the answer B is correct answer for good lasing. Lasing will happens in both E321 and E221 also,
Okay.
but this will give you very short pulse because there is no population inversion. Once electron comes here to here, that is okay. And also there is some metastable state, so maybe this electron did not go directly to E1, it will go through E2 to E1.
Yeah, that's fine. That is okay.
Hmm.
But actually, the confusion is there, like due to this hint here in this question, because it directly tells that the spectral line would be inversely proportional to the lifetime. So that's why the confusion occurred in my mind. Okay, I will just check it once.
Okay.
And another, like these two question, can you just tell me like how this thing is happening? Like question number one and question number, I think there is similar question. Question number three.
Question number 3. The student shines a laser light on the gas atom in cavity A with a square shaped pi pulse. At the end of the pulse, the
Oh, sorry. Just sorry. I This one I know because pipers of whole energy will be absorbed. So this one I got correct. I just had confusion with this question number one. Yeah, that
yeah.
I made wrong
So
here.
what is the question number? Consider a given volume of the gas with N0 equal to 100 atom and describe why the two level system having state 1 and 2 with energies E1 and E2. The population of the atom in each state are N1 and N2 respectively as shown in the figure 1. Okay, N0 is equal to N1 plus N2 is equal to 100. Then the what is the question? Okay, the number of atoms in each level at equilibrium and given temperature T is given Y. So in equilibrium, uh, what is the atom? So what is the formula for N2?
Yeah, that is given here. N1 to the power something.
Yeah, whatever the in ground state, N2 will be e to the power minus Eg by kT, right? And what you
Okay.
have selected? You have selected 150-50. No.
Yeah. Since it was written like it was in equilibrium, so
Okay. So in equilibrium, excited state and ground states are both filled equally.
no, that's not true. It depends on the temperature.
Eh?
It will depend on the temperature.
No. So then what is the temperature term role?
Yeah, that I couldn't manage. Like that's why I'm asking you. Like,
Yeah. So that is the right answer which they gave.
okay,
Maybe you should think if it is given the temperature and also the answer have two option with temperature term, then maybe it will be either of one.
okay, okay, sir. And this question we discuss. Okay, sir. Thank you.
Okay.
Uh,
So do you want that fabrication
Yes,
exercise?
sir. I just wanted to discuss with you. Actually, sir, there is some APM will go on from in our institute annual progress meeting.
Okay.
So can we fix that extra class in the next week?
Yeah, next week will also work because this is week 9, right?
Yeah, yeah.
So week 10, 11 and 12. So three more weeks left. In between, whenever you are free, you just tell me.
Okay, sir. Then actually, after the APM will be over, I will be available.
Okay.
So
So where
we
is
can.
your APM?
It is on 29th September.
20. Okay, then after that we have some meeting. Okay.
Okay, sir. Okay. Thank
Okay.
you. Thank you.
Bye.
Bye.